All right, let's do this. So we're going to talk about probability tonight. Of course, kind of everything we're doing is probability, but tonight's probably, I'm just going to come out and say it. I think this is my least favorite of the chapters, but we need, because really all we're going to do, the lab is going to be much more fun. But we have to define some terms in order to kind of build upon. So, some of this might be review, but I think it's worth the review. So it's just laying the foundation as far as I'm concerned for what we're going to do. Why can't I find the next? There we go. The question's still unanswered, or the big things here. So I gotta go and look at the details. I don't know what questions are still unanswered. Is what we have probably a few moments now, or we can also do it at the end. Is there any like burning questions right now that we should be that you want us to address? I got some notes. I think I tried to reply to the notes about the DAX. If you want to get back to your results, you're going to have to email us because in the last week or so, that the CUNY instance switched over to use single sign-on. So if you log in now, you're going to log in with your CUNY account, which is fine, but your results won't be linked to that account, though it will have been on an old one. So we can retrieve it still if you want it. So just let me know. We will get that and we'll update the I know I keep saying I need to update the Blackboard with those results. We'll get to that soon, or I'll get to that. All right, so probability. So at its core, right, we're talking about, the likelihood of some event occurring. And just sort of mathematically, we're going to define that as, P of A, where we use this kind of functional notation where we're talking about the probability of some event A occurring. And we're going to define that to a value between 0 and 1. So a probability of 0 means, it could never occur. And a probability of 1 means it always occurs. And those are often the least interesting problems, right? All the interesting problems are somewhere in between. And there are sort of two major interpretations of probability, or at least two that we're going to touch upon in this course. The bulk of what we're going to do is look at probability from a frequentist interpretation. And that's really, a frequentist is looking at the probability of outcome if, of a particular outcome given the possibility of seeing an infinite number of those events occurring. Right. So and we'll dig into defining this a little bit more in the next couple of weeks, but right. Because there's some properties here that we can leverage, but and we'll start looking at examples. And the beautiful thing about ours, we can simulate data and simulate lots and lots. Like we can't obviously have an infinite number, but enough that we can start seeing trends. And we'll try to understand what these probabilities are, and whether or not we trust it, or how much, what a standard error. But that's all predicated on this notion that we could potentially observe an infinite number of processes or random events. Now, Bayesians take a slightly different approach. So they interpret probability as a subjective degree of belief. And so, a Bayesian will often say, well, data is my truth. And so, they're going to try to attack the problem as, how often would I see what I actually saw, right? It's not based upon the notion of an infinite, this notion of infinite number of events, but like how often would I see what I actually saw, and usually tackle it through some kind of random process. It's been around for a long time. We'll talk about it towards the end of the semester. We have a whole lecture on just Bayesian analysis. But it really didn't come into popularity until the last couple of decades, when fast computers were readily available, because it tends to be much more computationally intensive. Whereas the frequentist approach is not, doesn't necessarily require the same computational power. In fact, way back when I took stats as an undergraduate, we just used plain calculators, and we had probability tables, where we can now just use R to do a lot of this stuff. So we have this notion, the first notion that we need to talk about is this, the law of large numbers, right? And so we're going to use a slightly different notation. When we're talking about a particular observation, we kind of put this little hat or caret on top of the P. And that's just an indication that that's an observed probability. But what we're always interested in is the true probability, population probability often. And so what the law of large numbers says is that the observed population or probability is going to converge to the true probability given enough observations, right? The more observations we have, the closer that's going to get. So classic example, we're going to flip a fair coin. If, heads comes up on each of the first 10 tosses, what's the chance of a head coming up on the next toss? Well, in this case, it turns out to be 0.5 because assuming it's a fair coin, right, each event is independent. However, if we flip the coins lots and lots of times, we are going to expect roughly the same number of heads and tails, right? So that's important. So the probability is still 50% on the next toss, right? And this leads to something called gambler's fallacy, right? So the law of large numbers, right, says we should have the same number of heads and tails, but it loses sight that each event is independent, right? So, okay, shoot, let me load this up real quick.
Professor?
Yes.
Just to reiterate on the frequentist and the Bayesian understanding of data. So the frequentist would be like the actual, would say like the probability of a coin is landing on heads is 50% because he'd assume a random process an infinite number of times. But like if nobody had ever heard of a fair coin before, a Bayesian might constantly update his beliefs as he's learning about this process of flipping coins.
That's exactly right. Yep.
Okay, thank you.
So, yep. And when we do the Bayesian, the example we're going to look at is exactly that. Each iteration or each additional data point is going to update our beliefs. The technical term we'll use is a prior distribution, but we haven't really defined distributions yet. But yeah, that's kind of our input. The frequentist is going to presume there's some known distribution in the background. Typically normal, but we'll get to that. Okay, so let's look at here's a little Shiny app that's let me get back to the slide. So this is in the Data 606 package. So you can run this and just try this on your own. There's a couple of parameters that we have on the left-hand side. So we have number of games, right? So and then we have odds of winning. So I'm going to have odds of winning as 2. So this is essentially simulating a coin toss. So you could say, if you get heads, you go up. If you get tails, you go down. And what we have here is a cumulative sum. So if we got heads, we add 1. And on the second toss, we got a tail. So we subtracted 1, another tail, subtract 1, another tail, subtract 1, then heads, right? So we have this cumulative sum. So with an odds of, 1 out of 2, right? And we would expect roughly the same number of heads and tosses. And so we can do this. We can click, start over and see different paths as we go through. And we want to look at is like, where are we ending up after 100, right? So we're never really, rarely are we going to be exactly at 0, right? But we want to start thinking about is like, well, how far away from that 0 do we need to be before we kind of think it's different? Of course, if we go to something like 1 out of 6, so consider a die, and you win if you get a 1 and you lose for anything else, right? So we can run this lots and lots of times and kind of see where we're ending up, right? And you kind of get the number up there. This last parameter here allows us to do up to 20 at a time. So let's go back to the coin toss, because I think that's a little bit more of an intuitive problem to think about, right? Flipping a bunch of coins. So here we see at the end, right, we have 20 different outcomes. Looks like we might have got 2 that actually landed exactly on 0, but we've gone anywhere from, little less than -15 up to maybe a little above 15, right? So there's some range here of what we get. And so what we need to start thinking about is, well, how far away from that do we care? So the law of large numbers is saying, well, after a lot of coin tosses, we should have roughly the same amount. And I'm going to come back to that in a second. There's a question. Will they generate different results for the same P of A, or is the approach better given what you're trying to determine? Johnny, can you unmute or maybe clarify? I'm not.
Oh, yeah, that was that question between the frequentist and the Bayesian.
Oh.
Like if, like I think using that example with a coin toss, if we, is there a particular reason to use one over the other, or can we, put the coin toss down the frequentist model and the coin toss down the Bayesian model, but at the end of the day, they'll return the same result?
They don't always return the same result. So the short answer is yes, and we'll go into some details so later. So there are certain problems that are easier to actually solve in a Bayesian approach. So often when you have less data, a Bayesian approach might be better. Or where you have lots of possible outcomes. So some of the famous examples where Bayesian has been used successfully is Alan Turing cracking the Enigma machine in World War II. If you know that story, right? Alan Turing created a machine in order to crack the Germans' code. Now the Germans changed their sort of encryption code every day, but based upon some prior knowledge and some expertise, they were able to use that prior information to reduce the space that they were going to search to try to find to crack the code, right? So that was very much a Bayesian approach, because the frequentist would essentially have to try every combination, but the Bayesian says, well, we know it should be in these areas. Another one is Bayesian is often used for search grids. So again, post-World War II, there were some sunken submarines with nuclear warheads or submarines that sank during the Cold War. And they would use Bayesian approaches to figure out where, which grids to search for, to try to hone in on where those submarines were. Basically, each time they search a grid, they would get some information, and they can update the models to try to, calculate probabilities of where the sub might be based upon trajectory and weather forecasts and stuff like that, where the frequentist again would kind of tackle that. So those kinds of problems are often better at Bayesian. And as you get into more advanced courses, you'll probably encounter other methods. So we'll learn about regression and types of regressions, and there are now sort of Bayesian approaches to that. And we'll talk about what like a naive prior often just means we don't know. We're not going to assign higher probability to anything. We assume everything is equal. A lot of times you do get to similar results, but and then in our DAX project that Angela and I have, we use a combination of Bayesian and regression for scoring the essays. And we have found for certain criteria, Bayesian works better, and other criteria, the frequentist regression models work better. So, but we'll get there. But I like your thinking. All right. So this is a fun little thing to go. So these next two slides, to me, are my way of trying to visualize the law of large numbers. So here I have a run of 1,000, and I end up somewhere around -30, right? And you look at this, it looks like there's a lot of noise, right? This is truly a random process going on here. And you're like, well, after 1,000 head, coin tosses, I ended up with 30 more of tails than heads. But what we need to think about here is, what is the possible range of values that we could have after 1,000 coin tosses? We theoretically could get 1,000 heads, in which case we might end up at a positive 1,000. We could theoretically get 1,000 tails, in which case we would end up at a negative 1,000. So this is kind of a notion of scale. So here The y-axis is kind of just needs to capture the sort of fluctuation in the number of heads and tails we had over the course of 1,000 runs. But if we take that plot and actually, set the y-axis here to negative 1,000 to 1,000, right? This line of the fluctuation of heads and tails is pretty close to 0, right? Visually, I think better than it was here. Of course, we had a little bit of fluctuation, but if we went to 2,000 tosses or 10,000, right? Probably would be very likely that line would be so close to 0 that we might not see it if we scale the y-axis appropriately. So this is sort of my attempt to kind of get you to visualize what we mean by the law of large numbers. Do more and more of these, right? There's going to be fluctuations, right? Because each event is independent, and you may get runs here, but you're never actually really due, right? You could fall off further. So kind of using some other vocabulary here that we need to. So we have disjoint outcomes, which means to say that they're mutually exclusive, right? They can't happen at the same time. You can't get a head and a tail. A student can't pass and fail a class. But you can also have non-disjoint outcomes, right? So these are things that can happen at the same time. So a student can get A in stats and econ in the same semester. So this is going to lay the foundation to how we're going to start to define distributions. So this week we're talking about probability distributions. We'll expand it to other types in the coming weeks. So a probability distribution simply defines all of the possible outcomes that occur with their probabilities. So the rules for a probability distribution is that each event needs to be disjoint. The probabilities need to be between 0 and 1. And the sum of all the probabilities has to equal 1 to be a fully specified probability distribution. So here's the most simple one we could define, which is flipping a coin. So we have the probability of heads is 0.5, the probability of tails is 0.5. We could define a probability distribution for flipping 2 coins, right? And so we could get a heads on the first and heads on the second. We could get 2 tails. We get a heads on the first, tails on the second, or tails on the first, heads on the second, right? Each of these has a probability of 25%. These are all disjoint, and the sum of all the probabilities is 1. Independence. I've used this phrase already. So let's define it formally here. So when we say 2 events are independent, if knowing the outcome of one doesn't change the probability of the other. So knowing whether or not the first coin toss landed on heads or tails doesn't give us any information about how the second coin toss is going to turn out. But in terms of card games, right, if you know the first card drawn from a deck is an ace, that provides information on subsequent pulls, assuming you pull a card and don't put it back, right? And that second, right, that lack of independence is sort of the premise for what's often called counting cards, right? You might have heard of that one way you could potentially win and say like blackjack in Vegas is if you can count cards, because if you see what cards have been played, that changes the probability as you go as additional cards are played, right? So you saw an ace, so well, the likelihood of another ace coming up is low. There was a whole movie and book that I forgot from MIT students who did this very thing, right? They could keep track of this. And so at strategic times, make bets because they knew the probability of their hand kind of winning was higher. Now, Vegas kind of got smart to this. So that what they usually do is they have lots of card decks combined, right? So that the change in that independence is so small to really not give much of an advantage. And plus it gets really, really hard to kind of keep track of as you go. But that's key, that independence piece. It's really important. So we could check for independence. If we're talking about, so in this case, this is like survey data, right? And oftentimes you're just going to have, so Alex is saying he's having trouble hearing. Is anybody else having trouble hearing? No. Okay. Thanks for chiming in. Okay, great. So here's, so this is survey data, and we want to know if two things are independent. So in this case, we're interested in people's perception of whether or not guns protect citizens. And we want to know, is the response to that question independent of ethnicity? Right? This is kind of a common problem you might want to do. And so the definition of this is we're going to say the probability of A occurs given that B is true, right? Which we're going to write this way, probability of A given B, if it's equal to the probability of A, which is the overall event, right? So in this example, A is the response to the survey question about gun safety, and B is ethnicity, right? So if that's equal, then we can say A and B are independent. So if we have data here, so we have overall of anybody who responded to the survey said 58% said that guns protect citizens. So this was in North Carolina. Those residents who say gun protects citizens, given that they are white, right, is 6.67. So whites, 67% of white respondents said that was true. Black, 28% of Black respondents said it was would protect, and 64% of Hispanics. So since the probability of A, so we could say the probability of protect citizens given Black, 0.28, is not equal to the probability of A, which would be this one, then we would say these are not independent, that there's a dependence between ethnicity and their response to this survey question, right? So you probably imagine lots of examples like this where, you know, it's almost kind of sort of our first step into looking for interactions. And when we get to regression. Now, so random variables are numeric values that depend on the outcome of some random event. So we usually use a capital letter X, right? So we're going to say the probability of X, capital X, equals, some lowercase x or equals some kind of value. There's two types of random variables we're going to work with, and that's discrete random variables. So these are random variables that only take an integer value. So number of credit hours earned this term versus last term, number of heads captured, heads on a coin flip, right? They're just counts, they're whole numbers. Then we have continuous random variables, which can take on decimal value. So this is cost of books this term versus last term, right? Because if you have a real number or an integer, a real number or a decimal number, and you take a ratio of decimal number, you're still going to have a decimal number. All right, got to pull up the next Shiny app. Second. So this is an interesting app. So this was actually an app I designed many years ago now for a psychology student who was interested in gambling addiction and was trying to, kind of exemplify the law of large numbers and the gambler's fallacy as kind of a treatment. But I think it's also kind of nice to demonstrate, what's going on here and kind of lead into something called expected values. So this is actually based upon real data, again, from years ago. I should update it. But in New York State, they published the odds of winning for scratch-off tickets. So this was a $1 scratch-off ticket at the time. And the odds of winning $1 was 1 in 15. So 1 in 15 scratch-off tickets would get you $1. 1 in 11 would get you $2. For some reason, winning $2 was higher than that of $1. I don't understand that, but that's what it was. All the way down. So the highest payout was $2,500, and the chances of winning was 1 in 618,000. Okay, extremely, extremely unlikely. So there's not a lot. You can change the number of tickets. I set it to 365. So the notion here is like, what if I bought one scratch off ticket per day? How much money would I expect to have won or lost after a year? And so what you can see here is we're just doing a cumulative sum. So it costs $1 per ticket. And this is a bad year. The most ever won was $10, right? But after 365 games, I'm down $216, right? And I could do another run. This year was better. I only lost 111. Here I lost 129. So this is a fun little app that you can go through every few semesters I get one that like some year that's good, but oh, here's one I only lost $5 at the end of the year. I won $100 towards the end, right? So you can do this a bunch of times. You can do 10 at a time if you want. But so far after a year, I'm never positive. Oh, here I won 100. If I quit early in the year, I would have been good. But then we can look at the histogram. So if we take what I'm interested in right now is what's my outcome after 365, after a year of playing cards, we can start looking at histograms, right? And this is how we're going to start defining uncertainty, particularly from a frequentist point of view, right? So we can do this a bunch of times and say, well, in this last year, I lost $142. We can look at the coin toss, like after so many games, like, well, in some years I might have more, but what is the average loss, and how far away from that would I have to be before I would expect something, a foul, if you will, or something wrong. So we can see here's the distribution. So I took the endpoint of all of those and displayed them here so we could see after, I guess I did 118 games. So after doing 118 games of 365, my average loss was $156, but I was everywhere from roughly 0 to 1 year losing. That looks like maybe 275 or so. So this distribution here is going to be very important. It's going to be something we're going to look at in much more detail next week and the week after. So Matthew's asking, how would I calculate the odds of winning money after putting in $1 every day? I'm not sure. So the way, if you want to chime in to clarify, so the way this works is I actually have a random process in the back and I subtract the $1. So, it might even be in the slide deck. Do I have the code in the slide deck? Did not mean to do that. I could show this code later, but I just essentially draw a random number between, I can't remember what the odds are, 1 in 618,000, and I use something called a modulus to look for division. So if I get 618,000, I'm going to add 2,500 minus 1. I always subtract $1. So on this one, every 15 times, this is essentially a break even. This would go up 1 because I always have to add that $1. So that's what this is doing, putting $1 in every day.
So that's what I understand. But then you saw how you just like kept running it, running it over and over and over and over again, and it wouldn't ever really be over.
Mm-hmm.
You never made money really.
Well,
what would be the way to calculate the likelihood of winning money if you were to put in $1 every day?
Oh, I got 1 year here. Eventually it happens. Okay. Yeah. That's the next slide. Okay. So that's the expectation. So what I'm trying to get to is, we're going to talk, and we won't actually get to that calculation this week, Matthew, but I think we'll get to it next week. So what I'm going to talk about, the expected value is going to be the average winning or loss that I would expect. Okay. Then we'll, put that in my wish list. So I want to go to this tab. Okay. Look at it now, the histogram. So I have that one big winning year. So to answer your question, right, we're going to need to talk about the spread of this distribution. And the spoiler alert, right, is we're going to learn about a principle or a theorem that indicates that this distribution should be normal. And because if it's normally distributed, there's a lot of properties we know about normal distributions. And so from that, we can calculate the likelihood of having a value above that. So hold that question until I think next week, because right now we're just going to talk about the center. And next week we'll introduce the notion of spread to get to that, answer that actual question. And maybe we can work that out. But for the center, right, this is the mathematical notation. So it's really just a weighted average. Okay. So this is the probability of each outcome times the value of that outcome. So in the case of this lottery, right, if we go to the odds table, right, so the probability of X equals some value. So that's this, the probability of X equal 15, probability of, I'm sorry, yeah, that's right. And then this weighted part would be this value, right? It's $1, $2, $4, $5. Okay. So we take that, so that gives us the expected value. Might help. Let's walk through an example. So here's a silly little game. We have a game where you win $1 if you draw a heart, $5 if you draw an ace, including the ace of hearts, right? We need to define that because otherwise we need to make sure these are disjointed because we need to define a probability distribution. $10 if you draw the king of spades and you win nothing for anything else. So it's often helpful to put this in the table. So here we're going to say heart, not ace, to make this disjoint all of them there, right? So heart, not ace, the probability of a heart, not ace is 12 out of 52. Okay. And what's the value? You get $1. Okay. Right. That dollar is this part of the formula. An ace, right? There's 4 aces in a card deck. So the probability of getting an ace is 4 out of 52. And we win $5 for that. Okay. King of spades, there's one of those, 1 out of 52. We get $10 for that. Right. And so we have 35 cards left. So 35 out of 52, we get nothing. So I put this here just to be complete because we want to define a complete distribution, probability distribution. So the sum of this column is 1, right? So if we look at this formula, so what we're going to do is the probability of each of those events times its weight. We're going to sum that. So we're going to do 1 times 12, 52, 1252, right? 5 times 4 over 52 is 20 over 52, right? 10 over 52, 0 times that is 0. So if we sum all that up, we end up with 42 over 52, or about 0.81. So in this game, you would be expected to win an average of 81 cents. Okay. Now, if it cost $1 to play this game, right, you would be expected to lose 19 cents per game, right? And so that's the key for, if you gamble, you go to Vegas or Atlantic City for fun, go for fun. But realize all of their games are weighted such that the expected value is negative, right? That's how they exist. So anyways, the only exception I think is poker because you're really playing against other people. And so that might be the exception. All right. And so we can look at this visually, right? So this is a probability distribution and we can display it here as a bar plot. So we see that the getting 0 is the most common, right? Over 60% of the outcomes is 0. About a little over 20%, you would get $1. $1. We have about 10%, you might get $5, and just a couple of percent, you get 10. Now, 6, 7, 8, 9, 2, 3, 4 get 0, right? Because those could never occur in this particular the way that this particular problem is set up. But this is a distribution. So the sum of all these bars equals 1, right? And so as we'll see, right, this is a distribution. And one of the properties of like these types of probability distributions is the area under all these bars. And when we get to continuous variables, it'll be a smooth line. But the area under the curves or under these bars is always going to equal 1, which is super handy, as we're going to find out, in order to infer probabilities of other events from these distributions. We could also do this through simulations. This one's not too hard to actually calculate out, but sometimes some problems are really complicated, so we might want to do it through simulations. So here I'm just creating a data frame that's with those outcomes, changing some names and making sure that they're integers. Okay, oops. Sorry, here we go. And so I'm going to do a number of trials. I do this M, which is the number of outcomes times the some of the odds, just to make sure I get all the possible combinations. I'm not going to go into details as to why that is tonight, but then I'm going to do the odds. I'm going to sample that many times or from that number 1,000 times with replacement, right? Because each event needs to be independent, which is why I have this replace equals true. So this sample function is going to give me a number between 1 and whatever this multiple is 1,000 times. So the length of this odds vector is 1,000. Okay. I'm going to create a vals, right? And I'm going to repeat -1 for however long this is. So this is also a vector equal to has 1,000 elements in it. Okay. Initialized to -1, right? So this is essentially simulating if I buy 1,000 tickets. But I paid that $1. Now, what I'm going to do is go through each row in this tickets variable, right? And if the odds, so this percent might not have seen before this. So this is a modulus operation. So essentially what this is going to do is take that odds value, divide it into the odds that I actually did from the sample. And if it's equal to 0, right, meaning the remainder is 0, then I'm going to set the value equal to the winnings, right? So if I get something evenly divisible by 618,000, I'm going to put 2,500 into the value. So the way this works out is I won $1, I lost $1, lost $1, and I just kept losing $1. But now what I have is the mean of this values is negative 58.3 cents. Okay. So we could do this through now. If I do it through the actual calculated way, the real value or the theoretical value would be losing an average of 38 cents. But if I rebuild this slide and rerun this code, I'm going to get a slightly different answer. So without trying to get too crazy, we could have a distribution of distributions, but simulations is a great way. And I like to show this as a way of trying to tackle some problems, right? I can see what the outcomes are, and I can just easily simulate data to get there. Oh, you can see here, I actually reran it on this slide, and I got 47 cents, right? All right. Questions about this. So this lays the foundation for building up probability models and distributions that we can then use in other contexts, including inference and regression and other approaches. But this stuff is oh yeah,
Professor, I have a question.
Yep.
So this might sound like a really ignorant question, but I just can't wrap my head around the fact that simulations are useful, because the way I see it, you're making up data, right? And you're actually inputting the probability vector, and based on your input, like data is being made up.
Yep.
So how can that be useful? Like you can just assume that it's going to be 45% probability, right? And you can make up your own data. Why is it useful?
Because couple of ways is assuming the randomization process is truly random, right? And that's kind of eschewing the potential issues of random number generation on computers, right? But I find simulations really a great way to, through a process that is known to be random, right, or assumed to be random, whether or not it fits what I actually observe, right? So I do this often where I want to understand the behavior of some process. So let me simulate some data, and I have one data set that I collected or got somehow, and I'll generate lots of these random samples to see kind of how it behaves. And in some ways it's in this case, it's truly a random process based upon probability distribution that I was given. In some cases, it's just, I'm just going to do this to, see how well it occurs. So I have this project I'm working on looking at, maybe Angela can help me out because I'm going to try to recall this on the IRR simulation stuff, right? So in the psychometric literature, and actually this will come up when you do some advanced modeling, there's something called intra-class correlation. It's often used as a fit statistic in predictive modeling, but in the measurement field, intra-class correlation is a way of measuring inter-rater reliability. In other words, you have human beings, or you have something evaluating something, and you want to know how well they are correlated with one another. Now, simple thing to do is you could just report percent rater agreement, right? That's the easiest thing to say. So I have two raters and they rated 100 things. So for us, it was essays, right? We had two, say we have two raters, they rate 100 essays, and they agreed on the score 80% of the time. Okay. So we would say the inter-rater reliability percent rater agreement is 80%. But the literature has said that you should use something called intra-class correlation, which is a much more complicated thing to calculate. And there are some features they say, but the literature is doesn't really give a whole lot of guidance on how to interpret the intra-class correlation. They say it's just better because it's supposed to take into account random agreements. So I built a simulation that would randomly build data sets where I would fix the percent rater agreement through the random process and say, okay, I want to generate a bunch of data sets where they agree 80%, 70%, 60%. And then calculate the intra-class correlation with that data, with that simulated data set to look at the relationship. And it turns out those two metrics are highly correlated. So if you want some details, I think, anyways, it's kind of a long way around to kind of show how simulations could be useful. So I don't know if I have the figures on here. There's a Shiny app, but yeah, so it generated, so we have these plots, and of course there's more than one way you can calculate intra-class correlation, which made it more complicated. But on this plot here is the x-axis is the intra-class correlation coefficient, and the y-axis is the percent rater agreement. Each of these points is a simulated data set given some parameters. And so at the end, right, I could see what that relationship is. So for me, it's a way of exploring how I think things should behave, and kind of see what the outcomes are. And in this lottery example, it's not hard because there's only 12 possible outcomes. So we could easily define the full probability distribution and actually do this calculation. But there's very often times where you might have pieces missing, or you have a lot of data sets or a lot of observations. And so a simulation might be a way to get a good estimate. And then, as you'll see when we talk about the central limit theorem in a couple of weeks, you can run multiple simulations to kind of hone in on what the true value would be.
Okay, I got a sense for it now. Thank you.
Yeah, but I know I did a lot of talking, but
Professor, I would just
Yeah.
add that sometimes, getting real data is just not possible.
Yeah.
Space flight is a classical example, right? You're planning a trip to Mars and you have never done a trip to Mars. So
Right.
you're simulating, collecting data,
Mhm.
and you're obviously modeling it with real physical processes.
Yep.
And the model reflects those laws of physics, but the data itself is completely manufactured.
A lot of, well, this gets into like forecasting stuff too. I think there's some forecasting models that will, simulate data. Like weather forecasts are often, we have input data and then we can simulate data given, these inputs. If we assume the barometer or humidity is at this level, you could do that and you can just tweak the humidity level and see how the simulated data kind of changes over time, for sure. Yeah.
There's a big trend now in terms of synthetic data companies. I think it's a big emerging field in terms of AI, actually, with like
Mhm.
being able to, like for autonomous cars, right? It's hard to simulate every single scenario. So I think they're using synthetic data to be able to train the cars. So there's definitely use cases for random data.
And it's sort of fitting because a lot of, this type of statistics that has been developing over the last century is trying to understand random processes. And so with computers, we can, replicate those random processes lots of times. And sometimes it's just, we think this is a random process. We see a particular distribution in our data. Well, let's simulate some data and see if the two agree. That's sort of kind of a way of doing fit. Oh, thanks, Josh, for the link. Other questions?
Question on that sample function. Is that based out of the stats module? And then in terms of, like sampling, like replacement, is that just like another parameter you could use?
Yeah, let's we can do a little example here. Okay, let me just create. So good question. It's a base R function, so it's just
Oh,
there.
okay.
It's in base, right? All right, I think I showed this last week, right? So we could have letters. So I could, if I just do sample letters, laters. Essentially, I'm just going to shuffle. Okay, but I could say sample letters. The second parameter is size, and I could say just give me one random letter. Okay. Now, if I say sample letters, size equals 30, I'm going to get an error because there's only 26 letters. I can't randomly select 30 from. So what I need to do is, if I really want that, is I could say replace equals true. Right. And so some letters, it might be easier to see it this way. So I could create a vector called coin. We'll say HT, right? So I could sample from coin, get heads or tails. I keep running it, right? I got heads, tails, but I always get 2, right? But maybe I could just say sample coin 1. So I just get 1 coin toss. There we go. And I could say sample, and what I was doing in the simulations is something like, I want to get 100. No, I'm going to sample from coin, but I want 100 of them. Well, that's not going to work unless I do replace equals true. So now I got a sequence. Okay, to show actually underlying what's going on, I'll call coin 2. What I was really doing is I was saying -1, 1. So if I sample from coin 2, right, I get this, and I reversed. So I could say save this to vals. I'm going to sample 100, replacement equals true, right? And now there's a function called cumulative sum. And you can kind of see.
Where it's
well,
just the total. Yeah.
Yeah, it's just adding up. So you can see I ended up at 24. So I could do that again. I ended up at 6, 6, 0, negative, right? Could do this over and over. Now, we got 10 minutes. So this is a good place to introduce this, then I don't have to do it as a post. Computers are generally bad at randomization, but there's, algorithms to do it. What you should be aware of, and this is going to come up, I'm going to try to preemptively answer a question. Oh, because I don't know if it showed up and I just didn't see it yet, but usually this lab, because you're going to do the look at hot streaks, Kobe's basketball stuff. And you're probably doing it interactively, and you're answering a question, and then you go to knit the document and you get a different number, right? Because you're doing some random processes in there. If you care about that, you can set the seed. So if so you can do set seed, and you could pick any number. I like 2112 a lot. And I do let's say, I'm going to just say sample something, a number between 0 and 100, and I just want one of them, right? If I do this, I'm always going to get 6 because that set the random numbers, but if I change the seed, now I get 41. Okay, so this is the input into an algorithm that should generate what looks like a random number. And to kind of see this, let's look at it this way. So if I create, I'm going to create a data frame, just call it, and I'm going to say X equals 1 to, let's go crazy. Let's go to 1,000. Okay. And I'm going to have Y equal, NA, yeah, integer. Let's do that. Okay. So, all right. So I have that initialized. So what I want to do, let me try to remember how I want to do this. So, okay. So I'm going to do this as a for loop. So I'm going to say for I in 1 to number of rows of data frame, I'm going to say data frame row I, Y is going to be equal to, say sample a number between 1 and 100. I need 1. Okay. But what I'm going to do here is I'm going to say set seed I. Okay. So what have I done? So I have X is essentially my seed, right? And I have 1,000, and Y is a random number between 0 and 100, setting the seed to X. Okay. So now if I do, I'll just do ggplot data frame AES X equals X, Y equals Y. I can just do geom point. Let's just do this. So if this is really random, this should look like noise, right? There should not be a pattern here, right? So essentially the X is the input to the random number generator, and Y is the random number that we get with that seed. Okay. I know we haven't talked about correlation, but probably you kind of have some intuitive sense. So I can do core.test on data frame X to data frame Y. And so the correlation is essentially 0, right? Which is good, right? It means there's no relationship between the seed and the output. But anyways, if you want to replicate something, you can always set the seed. And so when you go back and regenerate the random number, you're going to get the same random number.
Professor, just so I understand, set.seed is a random number, but
No.
it gives you the same random number.
No. So it's think of it like a seed, like you plant a seed. So the random number generator algorithm takes some starting number and runs it through a heuristic to come up with what's called a pseudo random number. Now, typically the seed is often like the number of the time in milliseconds whenever you call it, right? That is essentially a random number, right? So often you don't set it, but if you want to replicate exactly the same thing and you're doing some kind of sampling, setting the seed is really useful. So I'm trying to remember, there's a security company. No, who's the company that does denial of service protection?
Is it Cloudflare?
I think it might be Cloudflare. Let me see, Cloud. I think it might be Cloudflare. What are they? Lava Lamp. Yeah, look at that. It comes up as autocomplete, so that might be a. So Cloudflare has a wall of lava lamps to use to help into their random number generator. So great, because they're generating encryption keys. And so the way the lava moves in a lamp is thought to be a truly random process, something you can't predict, right? So yeah, so if you want this article, I just saw this recently, it cracked me up. Right. So that's that notion of setting that seed, like, because like I said, computers don't do random really. And if you do, the sample help documentation might tell you what. I don't know a whole lot of this. I'm not a computer scientist, but
So Professor, I have a question. If you move that set.seed outside your loop, what does your plot look like then?
Value would be one
Yeah, I
value.
mean, if you just set the seed to some number, just pick your 2112.
yeah, like
outside
this.
the loop. Yeah, but move it outside the loop, before the loop, yeah.
Oh, well, it's going to change, I think. Still noise because each sample is going to change the seed.
Yeah, because I would hope that the random number generator with just the seed set is random enough. And this sort of shows it that, just, you don't need to set it on every iteration.
No, you don't. No. And this is just, typically I just set it once at the top of the script. So look at the plot very carefully. Right. It's not changing. But if I comment this out,
Right,
it's going to change.
right.
Mhm.
So
But it's
what is the
still pretty
standard
random, which
in
is a
R
good
for
thing.
setting the seed?
Oh.
Is it as long as it's at the top of a page? That's like, because normally you could parameterize it like in a function. I guess in Python, that's how I think about it. But
Yeah.
for R, that's normally how you would set it.
Yeah.
Like,
I usually
you-
set it. I usually set it around where I'm going to do the random, my random selection. Only because every time I run a command, it's changing. So if I run things out of order, it could end up being different. But if you're in an R markdown file, you can just put it at the top and you net, you're good. Every time you net, because you're always starting at the top and you're running the same number of commands in between, you're okay. Some functions like random forest, if you heard of, like that has a lot of randomization going on in there. I do believe the random forest function, you can pass a seed into the function. Because that gets a little bit tricky when you have things that are parallelized, meaning they run on separate cores. So even if you set the seed when they fork, they might fork differently and the CPU may change. And so then the seeds could change. So it gets really complicated in some of those more complicated models. But anyways, yeah.
Professor, so it's set.seed is just a pseudo random number generator.
Well, the sample is the pseudo random number generator. The set.seed just sets the starting point for that random number generator.
So the set.c doesn't have to be 2113. It can be 49. It can be your favorite number. So that would give you a different starting point.
Oh, I see so it's only it's not the pseudo, I guess it's a pseudo random number generator for the first point in the entire loop.
Yep.
Okay, all right, thank
and
you.
I think it just increments after each sample. So the reason why I often, in this example, do the set seed I is just to be explicit, like we're incrementing the seed by 1 each time. And it still, has no relationship to the outcome.
Oh, I see what you're saying. You're taking I and it's giving you random number X. You're taking I plus 1, it gives you A.
Yep.
I plus 2 gives you Z. There's
Yep.
no one-to-one relationship.
Yep,
Oh, okay.
exactly. Which is what we want in a random number generator.
So sample 100 to 1 by itself is not random.
I think I can clarify here. I think what he's asking for is what the setSeed function is actually doing. And I think it's just ensuring that you get the same random numbers every time.
Yep.
Right? Because otherwise, if you knit it multiple times, you're going to end up getting different set of random numbers each time. And that could be detrimental to your analysis.
Yeah.
So it's basically like how you say values to variables. You can use setSeed to
Oh,
ensure that you get the same random numbers each time.
Correct. It's just initializing the random number generator. It's like a
Yeah.
variable, right? So if you have a
Yeah.
variable X in your program and you initialize it to 0 and you do your computation from that, you'll get a certain set of results. If you want exactly the same results, you better initialize X back to to 0.
That's exactly right.
So set seed is important when you want to replicate something, but if you want different sets of random numbers, then set seed, you probably won't want to set it.
A lot of times, well, it depends. Like, it depends on what you're doing. Sometimes I just do set that seed while I try to figure things out, right? I'm coding up my analysis, and I don't want, I'm trying to minimize moving parts. So that would be one. And then when I'm comfortable, when I'm going to do the final report, I'll turn the set seed off. But if I'm publishing a paper or an article, I often will set the seed because I want someone to be able to actually replicate it. They can come back and turn the set seed off to see if you get a different answer. Because to be fair, last week or the week when I talked about randomized control trials, I deliberately set the seed in that slide deck so that I would get an example where the effect was negative, because I knew on average it's going to work out, but I was trying to make a point. So I played with the seed until I forced that. So if you go back and look at the source code for the slide deck, you'll see that I did that. So when I build a slide deck, I always get a negative outcome. But I did it just to make an argument or make a point.
Okay, thank you.
Yeah, it's because this comes up in a lot of places. So and you're going to encounter as you work on this lab, you're going to probably write something up based upon interactive, and you're going to knit, and you're going to keep getting slightly different answers. They're not going to be terribly different, but slightly different answers.
Okay, thank you, Professor.
Yeah, no problem. Well, this is an interesting digression. I'm glad we had this, though. This will save me trying to write it up in Slack. As it comes up every semester. Just put it in the slide deck. So if your business is encryption keys, which sort of rely on good random numbers, the lava lamps are kind of cool.
Good night, Josh.
Yeah, good night. Any other questions? I put the 1-minute form in there. Give that a quick answer. All right, well, if there's no other questions, we can call it a night. We'll see everybody next week.
Take care,
Thank you.
Professor. Goodbye,
Have a
everyone.
nice night. Yeah.
Thank you.
night.
Good night.
Thank you. Bye.